Okay, thanks for attending the sessions I-20 on Android testing. Our first speaker is Ms. Jiwei Yang, okay, who is a PhD candidate in the Chinese Academy of Sciences. So, okay, Jiwei, would you like to go ahead?
Okay. Hello, everyone. I'm Jiwei Yan from Institute of Software, Chinese Academy of Sciences. In this talk, I will present the work entitled Multiple Entry Testing of Android Applications by Constructing Activity Launching Context. This is a joint work with the other 5 authors. Android applications are widely used in recent years. Meanwhile, the defects in Android apps arouse the attention of developers and researchers. Due to the event-based characteristic of Android applications, their test cases are usually in the form of GUI events. A great number of GUI exploration approaches have been proposed, including random, mode-based, and systematic ones. Despite using different exploration strategies, these approaches usually start their exploration from the default entry point of the target type. However, the single-entry testing approaches usually be unfriendly to marginal activities. For example, in this activity transition graph, the detail activity may fail to be launched due to complex gesture or logical operation. If that happens, the account activity cannot be visited either. Besides, the distance between the single entry point to each activity is unequal, which leads to an uneven coverage on the activity component. Using the single entry testing approach, it is also difficult for testers to launch each activity under their complex context. To address these issues and achieve the in-depth GUI exploration, we take each activity as a separate entry and propose the multiple entry testing approach. By extending single entry to multiple entries, activities could be launched by direct invocation instead of the long event sequences. Also, each entry should be will be tested completely under multiple contexts. There are 2 challenges for the multiple entry testing. The first one is how to design and construct the precise activity launching context. The activity launching context describes what we should prepare for the correct activity launching. In Android, several context-related information may influence the activity launching result, among which the ICC message is the most important one. For example, the ICC context for the search activity could be constructed by operating a set of GUI widgets or just by static code analysis. In this paper, we focus on how to generate context using the static analysis technique. According to the APIs provided by Android reference, there are 2 types of data items, including the basic attributes and the extra parameters. To construct ICC messages as ICC activity launching context, we should model all these data items correctly. For the string type data items, like the value of the basic attributes, we should collect their string candidate constraints for the model of the context. And the bundle extra parameters are nestable key-value maps. Like the picture shows, it has a structure. So besides obtaining their string type key values, we should also resolve and reconstruct their original data structure for the context modeling. And then for each entry, we will construct an activity launching model, which will be used to generate a set of activity launching contexts. And each activity launching context will then be transformed into a test case. To launch the target entries, we will generate a dummy application that contains all the test cases, which will be invoked for the entry launching and for the further exploration. Then our second challenge is how to perform the fair exploration using this constructed launching context. Because we have multiple entries, we have to make decisions on the exploration weight assignment of each entry. Here we use weight to denote the number of the exploration event. However, the importance of each entry is different, and for one entry, its weight also changes during the exploration. So in the weight assignment phase, we just take the activity launching result, the relationship among entries, and the dynamic changes into consideration. Let's look back to this example. There are three subviews of the activity transition graph. According to the activity launching result, we separate activities into successfully launched one and failed to be launched one use different color. For the successfully launched ones, they will be taken as the available entries, and for the failed to be launched ones, we expect these activities could be explored in the further exploration. Therefore, our weight assignment will assign higher weight to the entries that have larger subviews or are more possible to reach these unvisited activities. In this example, if we use the single entry testing approach, we will assign all the weight to the default main activity. But if we use the multiple entry testing approach, the weight will be assigned to all the available entries, and they will be updated adaptively. Then let's see the framework of our tool FACS. First, it pre-processes the APK file by exposing all the internal activities to exported ones. Then it performs static analysis to construct both the activity launching model and the activity transition graph. The activity launching model will be used to generate ICC context as well as a dummy application. Because of the generated test cases can only launch the target entries without further exploration, we call this strategy as FACS launch. Besides, we have another strategy called FACS exploration, which explores from the available entries according to their weight and under a specified exploration strategy. FACS supports multiple round testing, so during the exploration, it will collect the runtime information for the updating of both the activity transition graph and the weight calculation. In our experiment, we measure the effectiveness of the activity launching, app exploration, as well as the crash detection ability of FACS. We compare FACS with tools app, IntentFuzzer, Monkey on 20 popular open source apps from GitHub. This is the result of the activity launching coverage. After 1 hour testing, we can see FACS can cover as well as can successfully launch more activities than other tools. And this is the result of the method coverage compression. In our current implementation, FACS use the same exploration strategy as Monkey, but it extends the entry of the Monkey from single to multiple. And the results show that FACS outperforms Monkey on 18 of the 20 apps. Finally, FACS behaves well in revealing hidden bugs. By using the strategy FACS launch and FACS exploration, it can successfully trigger over 700 unique crashes, including 180 errors and more than 500 warnings. Among the 46 crashes reported to developers, 33 of them have been fixed. In conclusion, in this paper, we propose an activity launching context constructing approach and a multiple entry testing framework. Our tool FACS is available on GitHub, and more details could be found in the paper if you are interested. Okay, thank you.
Thank you. So, okay, we'll open the floor for questions. So I have a couple of questions for you. Could the activity launching context constructed be invisible? That is, the context do not corresponding to real execution.
Yes, that there may be invalid data generated. Yes, the invisible ICC context. Actually, we trigger a lot of crashes using FACS, and we separate these crashes into errors and warnings. For the errors, they are real bugs. because they are triggered from the exported activity. So this data can be triggered by in the real use. But for the warnings, they are triggered from the internal activities. We just exported them for the launching, and the SCC context constructed for these internal activities may contain some invalid data that may really happen. But we believe that this invalid data may make sense to the developers. That means they should pay attention to these warnings because when they add the new SCC colors or when they change the status of the explorer of this activity, new bugs will be introducing. And we think it is like a bit like the unit testing. Developers should pay attention about that, but they may also ignore that. It's okay.
So, okay, another question. In RQ3, you have identified RQ3, the research question 3. You have identified 719 unique reported crashes, right? And how many? Okay, why the number of unique crashes reported by FACS is much more than those reported by other tools?
Yes, because we turn all the internal activities to external ones. That we take all the activities in the app as the launching target, and we generate a set of contexts to launching them. If they do not process this input data, invalid input data, they may trigger crash, but these crashes may not really triggered by the exploration start from the single entry point, or they may just not be covered.
Thanks, you. Okay, time is up. Okay, thanks. So may I invite our next speaker? Okay, Zhen Dong.
Yes.
Are you ready?
Yes, I'm ready.
Yes. Okay. Our next presentations will be given by Zhen Dong from National University of Singapore. He will present to us, okay, nice piece of work, time travel testing of Android applications. And this piece of work also received the Distinguished Paper Award. So let's start.
Okay, thanks for the introduction. Okay, hello everybody. Thanks for attending the talk. I'm Zhen Dong from National University of from Singapore University of Singapore. Today, I'm going to present our recent work, time travel testing of Android apps. This is a joint work with Professor Marcel Bimmer from Monash University and Lucia Kojukaru and Professor Abik. So today, mobile apps are everywhere. We use mobile apps almost in every aspect of our daily lives, like food, traveling, business, shopping, communication, and so on. So mobile app testing becomes very important to make sure apps we are using work reliably without crashes and hanging, something like that. And the idea of mobile app testing is to generate a series of input sequence and feed them to the app and test. If the app works incorrectly, then the bug reported. And until now, there's so many techniques has been developed and they achieved a promising result. However, most of these techniques focus on input sequence generation. For instance, search-based techniques, they start execution with a bunch of random generate input sequence and mutate them with the hope to trigger new program behavior, eventually achieving more code coverage or find more bugs. Unfortunately, these techniques face a challenge to find bugs in deep state. Then these techniques often generate a lot of input that reach easy to reach area, but very few input that reach deep state. So let me illustrate this with a map of a popular game, Super Metroid. Probably most of generated input reach area around entry, and less input reach the middle area, and rare input reach the area at the end. So this kind of lead to a phenomenon that easy to reach area are intensively explored, but deep state are not explored adequately and leave bugs in deep state uncovered. So such techniques like search-based techniques address this challenge by performing a selection over input sequence. They select input sequence that trigger a new program behavior for mutation, hoping to generate input sequence that trigger more program behavior. But this kind of a input sequence selection for hitting deep state can be insufficient. For example, here's an input sequence that leads to a deep state, and this sequence is selected for the mutation. However, they don't know which part of the input sequence touch the deep state and trigger new program behavior. And especially for the input sequence is very long, for example, 100 inputs in a sequence, and the part of the input sequence that leads to the deep state can be broken during a mutation. And this is resulting in that the generated input sequence cannot reach the deep state anymore. So to address this challenge, we propose a time travel idea where we directly save the program state instead of saving input sequence. And the idea works as following. After the execution is launched by the testing tool, and we observe each visit state and save the state that are deemed interesting. I mean, interesting here is, the state has the potential to trigger new program behavior. And we save that interesting state. And when the execution goes along, then maybe the progress goes slow. Then the execution, for example, keep looping a certain state. Then we terminate the current execution and restore the most interesting state previously we saved and launch a new execution. So figuratively speaking, the testing tool can travel back in time to explore a previous state that is different input. So in such a way, the new program behavior can be kept explored, and a deep state can be identified and saved during execution, and they can be systematically explored by restoring them. So the bugs in deep state can be found. So our time travel idea is designed to enhance existing technique. As we see, our technique mainly consists of 3 components: the interesting state detection and progressive state detection. For interesting state detection component, check whether a state is interesting using code coverage and state information collected during execution. And progress detection component, monitor recent visit state, check whether the progress is slow. For example, the execution falling into a state loop, and its progress state selection components maintain the program state and select the most interesting state when the time travel occurs. And our framework is highly configurable. So strategies such like an interesting state and like a program detection strategy can be configured by users. So we implement our time travel idea into Android Monkey and call the tool Time Machine. And so to achieve a high efficiency, we identify the program state at Android side and maintain the program state at the desktop side. And maintain means we save the program state and already restore program state as a desktop side. And more importantly, we put the whole framework into a Docker container such that we can easily launch many containers for parallel execution. Okay, let us go to the evaluation. So in the evaluation, we answer 3 research questions. The first one is, how effective is a time travel strategy? The second one is, how does Time Machine performs compared to a state-of-the-art techniques on open source standard benchmark apps? And RQ3 is, how does Time Machine performs on industry apps? So for RQ1, as we see, the Time Machine achieves a significant improvement over baseline tool Monkey, and in both code coverage and the number of detected crashes. So that means the time travel strategy is effective to finding more code coverage and number of crashes. Okay. So for RQ2, we compare Time Machine with Sapiens and Stoat with the 2 recent Android testing tool. And the result shows also Time Machine achieves the best performance in both code coverage and the number of found crashes. For RQ3, as we see, the Time Machine achieve the best performance on industry apps as well. Okay, this is the evaluation. Okay, let me conclude here. So our research shows that saving and restoring state goes a long way towards a more systematic exploration of the state space. And our time travel framework is publicly available and can be used to enhance existing techniques such as random testing or search-based testing to techniques. Okay, welcome to use it. Thank you.
Thank you very much. So we welcome questions, and we have questions coming in. What is comprised in the state? For example, does it include the state of the file system or external resources?
Okay, I have a backup slide for the state identification. Generally speaking, we use GUI layout to identify program state. Typically, there are 4 levels of state abstraction, GUI state abstraction. First level is kind of a package level. Then you just compare the package whether the same or not. If different, than the new state. And then this activity level. Then if the activity changed, then there's a different state. The level 3 is layout, a widget layout comparison. If any layout of the widget is changed, you identify as a new state. And the level 4 is kind of more fine grained. They'll consider all the text in the GUI layout, in a GUI widget. For example, text box, if the number changed from 1 to 3, then you also consider new state. Then there will be a lot of state. For example, you can tap any number in the text box, then it goes a lot of state you cannot handle. So in this, in our work, we choose the level 3 as our state identification. Then here, for this level, we can distinguish 2 screens as a different state. If there's some layout change, for example, here, then the layout change. But for these cases, for example, just some value is changed here in text box, then we don't consider it a new state to make it the state exploration issue.
Okay, another question is, okay, are there any kinds of states that cannot be restored by your technique?
Sorry, any state cannot be installed by my technique?
Yes, by your technique. Are there any kind of states that cannot be restored by your techniques?
Actually, I don't have some issue because I take the whole Android system as a snapshot as a state. We take snapshot of the whole Android system as a state. So whenever I take snapshot of a whole system, I can restore it. So I don't have some issue like this.
So, okay, the next question is, how can you access that time travel reaches deep states?
That one, I just used deep state or rich state. This kind of a general concept. In the work, I don't actually define what is deep state. I define the interesting state. The interesting state is means it has the potential to trigger new program behavior. For instance, a state that never visited before, then that has a potential to trigger new program behavior. On the other side, actually, when you from a state goes to another state, then some new code is covered. This means some new functionality in the app is enabled, so you can test it. So that means you have a potential to trigger new program behavior. So we consider those states are interesting. We give them a strategy to explore those states further. But for deep state, actually, it's kind of very general concept. I don't define exactly in this work.
Okay, thank you, Zhen Dong. Okay, time is up.
Okay, thank you.
Thank you. So may I have a next speaker, Xin-Hui Tan. Xin-Hui Tan is a faculty member of the Southern University of Science and Technologies. Okay, Xin-Hui will present her work on collaborative bug finding for Android apps. Xin-Hui, are you ready?
Yes, I'm ready.
Okay, so, okay, please go on.
Okay, thank you for the introductions. My name is Xin-Hui Tan. This work is a joint work with my students, Chi-Chang Lee, and both of us are from Southern University of Science and Technology. The topic for today is collaborative bug finding for Android apps. I would like to start my presentations by giving you are motivations. There is a studies that aim to answer the questions, how do developers test Android apps? We realize that developers unfortunately have not found any easy to use testing solution for Android apps. Well, another developers mentions that a lot of what the developers is doing is about how the app is looking and feeling. Therefore, a lot of testing is still done manually. So in this study, it's concluded that developers mostly still rely on manual testings and unit testings. Meanwhile, developers also say that they actually prefer automatically generated test cases in natural language. At the same time, all of us may be familiar with the fact that there are many bug report access in repository like GitHubs. In these two examples you see here, app developers who develops Pocket Hubs and Fort Hubs, which are both YouTube clients, they're actually able to find similar bugs across these two apps. Well, this is quite expected because these two apps have a lot of similarities. Let's see an example where you can see that in the left-hand side for camera color pickers, that's what it say, it's trying to pick the colors from the cameras. And the one on the right-hand side, Uno Cache, that try to help users to manage their financial budgets. When we look at their bug report title, it's quite surprising that there exists almost one-to-one
It sounds like the network connection is broken. Xinhui?
Yeah, I think we need to play the backup video. Sorry for the interrupt.
Sure, please go ahead.
Yep. 안 들려요? I'm sorry now. I think there is a sound problem.
So the presenters come in. Okay, then let's try. Okay, try again. You try again. So maybe we need Xinhui to continue the live presentation. Xinhui, are you okay?
Yeah, I will try to open the presentation again. I don't know why it's closed. Okay, let me resume the presentation by sharing the screen. So I will try to. So in this example, we can see that there exists, for example, in the second rows of the bug report title, we see that both of these apps rely on Gradle for compilation. So they need to make sure to make the Gradle.w file being executable. Now you may be wondering what is so special about bug reports. Bug reports contain what we call test scenarios. Test scenarios include things like steps to reproduce the behavior. And more importantly, it includes something like test data that can be quite difficult to generate automatically. For example, image for an image processing app, or here in this example is a node. Another interesting things, including in the bug reports, is the expected behavior. This could actually help us to solve the test oracle problem that existing automated test generation approach will not be able to solve. We introduced the concept of collaborative bug finding that's inspired by pair programming, where we try to emulate the role of a competent programmer with developers of similar applications. That is, well, in traditional pair programming, they have the roles of navigators and drivers, where the drivers will drive through the bug finding or typing coding process. The navigator will be looking on the screen and then seeing what kind of errors that the drivers makes. We have the same concepts here in bug finding, where other Android applications serve as navigators, and the app under test is serve as the drivers. Let's look at how collaborative bug finding works in classroom settings. I was teaching a class, the software testing class CS409, with 29 students using GitHub Classrooms for their class projects. In the class projects, each student need to select one app for testing, and we try two settings for the collaborative bug finding. In the first settings, students actually share the bugs that they found in GitHub discussions, and other students read these bug reports. In the second settings, the coder was a manual issue settings. The students actually need to manually search for relevant GitHub issues. Let's look at an examples where the students find bugs. This is the example that you have seen previously. What happens in this example is that there is a node that is being added, and then in this node that is being added, we add a new category and then add this node to the newly added category. What happens is that the counter is not being updated correctly. Reading these issues, another students actually find what we call a derived issues. Well, this apps here is a new pipe apps that is aimed to watch YouTube videos. But in this scenarios, we find that when you're trying to import the subscription files, while the import error message or the dialog box is shown correctly, the imported content has not been shown immediately. So it turns out that these two apps have the same issues. That is, the view are not being immediately updated, and we will only update the view after restarting the apps. And this is actually a prevalent problem that affect many apps. Because students actually complain that while collaborative bug finding is quite inspiring and help them to find bugs, it may be quite time consuming to search for relevant GitHub issues. Hence, we propose what we call bug genes that aim to recommend similar apps. That is, for the app under test, we're trying to see whether the app in our database shares similar GUI components, and we recommend the bug reports that mention the shared components to the apps under test. If you're interested to know more about bug genes, you can visit our posters that is presented 2 days ago. Now let's look at the effectiveness of bug genes. Turn out that bug genes is quite good bugs, and
Sounds like there are problems with network. So since, okay, the time is almost up, so may I invite the next presenters to join? Chen.
Yes.
Okay, good. So our next presentations will be given by Chen, who is a researcher from Nanyang Technological University in Singapore. And Chen will share with us his work on an empirical assessment of security risks of global Android banking applications. Thank you.
Okay.
Okay, go ahead.
Hello, everyone. My name is Sun Chen from Nanyang Technological University. Welcome to my presentation, an empirical assessment of security risks of global Android banking apps. As we all know that financial service apps such as banking apps are widely used in our daily life and have changed our lives. People use this app to conduct financial services such as transfer funds and pay bills. However, vulnerabilities inside this app will pose severe security threat to mobile users, and attackers can exploit these vulnerabilities to steal users' money and users' sensitive data. According to a recent report, 70% of top 100 mobile banking apps are vulnerable security attacks and data leakage. Okay, let's see a real example. A banking app named Gcash with 10 million downloads on Google Play. And when you first use this app, you need to register this app. You should input PIN code, first name, last name, and your address. However, all of this sensitive data will be sent by SMS and also will be saved in the SMS outbox. And meanwhile, all of this data will log the output. Therefore, attackers can exploit these two vulnerabilities, SMS data leakage and login data leakage, to capture the sensitive data from mobile users. Motivated by the above observation, we aim to conduct such a study to investigate the overall security status of global Android banking apps. And we also aim to investigate the global distribution and the multiple version analysis. And we also investigate the weakness fixing process. Consequently, we can provide fixing recommendation, useful findings, and we will also can unveil the gap of the vulnerability understanding between industrial and academic. And we highlight the lessons learned based on our study. And according to our previous study, we know that industrial developers and users pay more attention to the data-related security weaknesses. Therefore, in order to collect a high-quality data set of data-related security weaknesses, we need to conduct a comparison study on the existing tools such as Android Bugs and Mobile SF. And after conducting an in-depth comparison study, we know that the existing static security assessment tools most focus on pattern-based tracking, and they always output a lot of false positives. They always provide hundreds of vulnerability candidates to developers, but developers cannot use their candidates directly because they don't know which one is the real vulnerability in their candidates. And last but not least, they cannot be used to detect most of their data leakage related vulnerabilities. So we need to develop our own tool. Before that, we need to propose a taxonomy of data-related security weaknesses. After conducting a literature review based on the academic papers and industrial technical reports, we propose a taxonomy which contains 4 main categories and 22 security weaknesses. And based on the security weaknesses, by leveraging static program analysis, we propose an automated security risk assessment tool named Auth0. And Auth0, giving a banking app as input, Auth0 uses a forward data flow analysis to identify what the sensitive data is, how to trigger the leakage, and where the data is leaked. And we also use a backward control flow analysis to reduce false positives by eliminating that code inference. We also combine the pattern-based approach to examine authentication and encryption security weaknesses. And due to time limit, if you are interested in the technical implementation, please refer to our X paper. At further evaluation part, we select 60 banking apps as our comparison subjects. As shown in this table, we can see that Auth0 achieves the best performance, not only the number of security weaknesses, but also their precision. Sorry. Today, I will take more time on the assessment results. We make substantial effort to collect 693 global banking apps from over 80 countries, and we assign all of these apps by or zero. We got over 2,000 security weaknesses, and there are 592 cases of sensitive data leakage. And even worse, there are 82 cases of credentials leakage, such as PIN code and password, which will cause severe user-sensitive data leakage. And when it comes to the communication security, we found that 222 apps are using invalid authentication, which will cause severe man-in-the-middle attack. And besides their overall security status, we also conduct a global distribution analysis. And as shown in this figure, different colors represent the severity of security status. We can see that Asia and South America have the severe security status, and Africa has a better performance because some of financial services date from Africa, and Africa has a long history to use their financial services. And we also conduct a multiple version analysis. Note that banks always develop the different versions for different countries. So we assign all of the country versions for the top banks. We conclude that app security weaknesses vary across different markets by countries and bring fragmentation problems among different versions of the same bank apps. And this observation is evidenced by the South Korea versions of Citibank and the Chinese versions of the HSBC. And because these two versions contain more security weaknesses compared with other country versions. And actually, the vulnerability reporting process is inefficient, which causes several months and hundreds of emails. How about the patching process? Actually, until now, 21 banks have confirmed our reported vulnerabilities in different ways: active response and silently patched. And among them, 10 of the banks have confirmed our reported vulnerabilities by emailing us positive feedback. Seven of them have patched the vulnerability, and the remaining 3 claim that they will fix our reported vulnerability in the next release version. However, in another 11 banks also indeed patched our reported vulnerability, but we don't receive any response from them. In summary, for the 126 vulnerabilities, 52 vulnerabilities have been patched, so the patch rate is 41.27%. And when they fix the reported vulnerabilities, 5 new vulnerability introduced in the release new version, which indicates that the security assessment process is immature for the industrial banks. Here we highlight the feedback from industrial vendors. We received 114 emails from them, and we conduct 7 in-person or online meetings with them to discuss the report details and help them to improve the security of their mobile banking apps. And we highlight that we received acknowledgement letters from industrial vendors such as HSBC in UK and OCBC in Singapore. And we also help them to improve the security status of their new release versions. And last, in the future, we will focus on the security risk assessment of Android apps. And we will take more components into account, such as source code vulnerability, third-party library vulnerability, and the native code vulnerability. We will aggregate all of these components and provide a security vulnerability report. And we will also provide a security risk score to the industrial developers, users, and other customers. Okay, that's all. Thank you.
Okay, thank you. Okay, for the presentation. There are a couple of questions. The first one is, okay, have you conducted similar studies on iOS applications?
Actually, we have some studies under iOS security, but until now, we don't do the same things under iOS apps. But I think it is an ongoing project for our lab. We will pay more attention to the iOS security because the researchers pay more attention to the Android security, but they don't. It is difficult to analyze the iOS apps than Android apps. So we will pay attention to the iOS apps. Yes.
Okay, sounds like I have some problems with pulling the questions. Okay, anyway, there's another questions. Let me check. Right. In the research question 5, what do you think are the possible reasons that about half of the vulnerabilities that are not patched, even though the corresponding apps are patched?
Yes, there are many reasons. The first one, I think I think there are many. There is a big gap of vulnerability understanding between industrial and academic, because we reported some vulnerability to industrial vendors. They pay more attention to the data related security weakness, but for some of their types, they think it is they are not vulnerabilities. For example, they think all of the developers are using the MDU and hashing to encrypt the data. It is not secure. It is very secure to do that, but they don't think it is a real vulnerability. But after we conducting an in-depth discussion, they think, okay, that also insecure. We need to patch this vulnerability. But this is a long way. This is a long road to discuss and help each other, I think.
Okay. Did you assess any third-party finance apps such as Alipay, PayPal, and so on?
Actually, as shown in this this figure, we focus. We not only focus the source code vulnerability scanning. We are also focused on the third-party library vulnerability. And until now, we found many vulnerable third-party libraries inside the host apps. And I think some many CVEs inside these third-party libraries and and the apps will vulnerable the third-party libraries. So I think the third-party library security is have the similar security attention to the source code vulnerability. Yeah.
So, okay, thanks. Okay, okay, sentence time is up.
Okay.
Maybe we have the next speaker, okay, Zhu Qian, join us. So, okay,
Hello?
Our next presentations will be given by Zhu Qian, who is a researcher from Nanjing University of Aeronautics and Astronautics. Okay, he will present with us his latest work on Roll Script, a visual script-driven, truly non-intrusive robotic testing system for touchscreen applications. Okay, Zhu Qian, okay, please go ahead.
Hello, everyone. I'm Zhu Qian from Nanjing University of Aeronautics and Astronautics, China. Okay, I will start my presentation. Let's firstly take a look at the background. This work we focus on the test automation for touchscreen applications. A typical way for such kind of test automation is to firstly record many actions as test scripts, and then we can use test tools to automatically execute the test script. The typical tools for such kind of test automation include Robotium, Goguryeo Automaton, or Apium. A problem of these existing techniques is that they are intrusive to the device on the test. The reason is that they depend on the operating system or GUI framework of the device on the test to either get GUI states or trigger GUI actions. And because of this reason, we need to install agent software on the device before testing, and we need to build wired or wireless connections to the devices during testing. So since we need to at least make some changes to the internal of the system, I install software, and we consider such kind of test automation is intrusive to the device and test. And a problem of being intrusive is that intrusive test automation is difficult to work on closed or uncommon systems. For the closed systems, an example is a GoPro camera and the Nintendo Switch game console. In such kind of system, there's no way to access the internal operating system of GUI framework. Therefore, it's difficult to conduct automatic testing. And for the uncommon systems, a typical example is the embedded system with VxWorks-like operating system. In such kind of system, unlike Android or iOS, it is difficult to implement a test agent on such system to enable test automation. So since intrusive test automation is difficult to work on many platforms, our objective is to build an easy to use and truly non-intrusive test automation system for touchscreen applications. More specifically, we want the approach to not require to build connections to the device during testing, and we want the approach to not require to install any software on the device before testing. So our work starts from a simple insight that by combining video GUI testing and local technicals, it might be possible to build such an easy to use and non-intrusive test automation system. Video GUI testing was originally invented in Security, and it largely uses widget images to express the GUI actions on touch screen. And such images can be easily obtained in a non-intrusive way. And with local technicals, we can trigger the GUI actions while logged from the external of a device without to install anything on the device on test. So although the inside looks simple, there's some challenges in building such a kind of test automation system. One is how to express various local-based test actions in video test scripts. And then is how to non-intrusively execute the video test scripts with the robot. And third is how to non-intrusively record GUI actions on touch screen. Keep in mind that we want all the solutions to fit the non-intrusive context. So we address these problems by introducing low-script video script-driven robotic testing system. Here's a picture of our system. The core part of our robotic testing system is a XY plotter, which is widely used in personal writing and drawing. And we use a camera to obtain the GUI states, use an XY plotter to trigger GUI actions. And in low script, we introduce a test script language. The language uses camera taken pictures instead of obtained from OS. Use camera taken pictures to build test scripts, and we introduce new instructions for robotic testing. And we design a test engine. The test engine can turn high-level video GUI test scripts into low-level local commands. We use open source EBB command set to drive low-level local motion. And we take several steps to enable fully automated test execution. We first locate widgets on the screen, and then we determine the move of the locked arm, translate the move from the image space to physical space. And we perform GUI actions, and we make a deter to make sure the locked arms will not cover the screen between different actions. And we also introduce interesting test script recorder. The recorder can non-intrusively record test scripts from human action videos. So given the human action video, record our finger action on a touch screen. And we can take several steps to turn that human action video to a test script. So our first step is to using skin color-based hand detection to find the hand on the screen and to locate the click position. Then we also introduce algorithm to crop widget images, find the widget images automatically, and then we build a test script from the cropped widget images, so we can turn the video into a test script. And we finally conduct an evaluation on many different devices. First is to we validated the flexibility of this low script enabled test automation. We find that low script works on at least 6 devices, 3 cell phones, a Windows tablet, Raspberry Pi, a Linux-based Raspberry Pi, and GoPro camera with on system. And it works on 21 applications, more than 600 GUI actions and 40 widget action combinations. And we evaluated the accuracy. For the accuracy in performing touch screen actions, we find the success rate of low scripting accurately triggered GUI actions is over 90. And for the efficiency of performing touch screen actions, we find triggering a GUI action by the robot cost about 6 seconds. For the accuracy in recording click actions from human action videos, we find that low script accurately record about 84% of click actions into test scripts from the human action videos. We also compare low script with the intrusive test automation tool SQL. We find that the accuracy and the speed of low script is lower than SQL. So low script sacrifice some execution speed and accuracy for being truly non-intrusive. So okay, finally, let's make a short conclusion. We propose introduce a new truly non-intrusive robotic test automation system. We provide a video-based script recording technique. We do a comprehensive evaluation of the proposed robotic testing technique. And there's still some limitations in low script because the execution speed is slower than intrusive testing, and sometimes the low script does not accurately perform GUI actions, and the low script do not support automatically record arbitrary GUI actions. Now it only supports for clicks. Actually, we since the IC's paper, we have significantly reduced the many limitations recently. For example, the speed, we have significantly improved the speed. So that's all. Thank you very much.
So thank you, okay, Zhiqian, for the presentations. Now we welcome questions. Okay, Zhiqian, there's a question for you. Could you compare your approach with one using VMs, virtual machines?
Virtual machines. No, we haven't compared that. We use real device to conduct the testing.
So do you expect, okay, there are different effects or there are different kind of bugs that can be detected by raw script, but not by using virtual machines?
There actually some application you cannot find a virtual machine for this. It's difficult to find. For example, if you want to test a camera, it's difficult to find a virtual machine to run the applications in the camera. For example, if you want to test a Nintendo Switch game console, you want to test the game, you are not able to find a virtual machine for such kind of system.
Okay. Next question. Do you need to prepare a video for each specific operating system? Or the video is generic that can be used for all kinds of operating systems?
Yes, our video works. Our script recorder can work on all these systems, all these cell phones, tablets, and Raspberry Pi and camera. We have some simple instructions for the action. However, the video can be recorded for any of these touch screen systems.
Okay. Okay. Does it mean that you need to prepare a separate video for separate operating system?
Yes, we for each actually, if you want to record a test script, we need to prepare a video for the test scenario. A user need to operate on the device to repeat the test scenario, get the video, and we then can use an algorithm to turn the video into a test script. So at least we need to record a video for this test scenario. On any system, if you want to record a test script, we first need to record a video for the test scenario that you want to make a test script for it.
I see. Okay, in fact, there are many Android device models and apps that one on one device may look a little bit different when it runs on another device model. So does row script need to recapture the test script for each device model, or it would automatically adjust for different kinds of device models?
Actually, given us test script, this test script is binary to a device. So if we want to test Android, we record the test script for Android. So there, for the same application on iOS, there's actually maybe can be some difference. So there's no guarantee that the test script will work on Android or on iOS. At least it can still work on Android. On the
so even for Android, there are different Android device models. Okay, some Samsung.
If they have the same UI. They use the same UI, and we can repeat that. However, we in the experiment we haven't tested that in the evaluation.
Okay, thanks a lot. Okay, Zhijian. So time is up, and thanks for attending the I-20 sessions on Android testing.
Okay, thank you very much.
Okay, thank you. Bye-bye.
Thank you very much.
Hello, welcome to the session I-23 on code artifacts analysis here at ICSI 2020 online. We will have 6 presentations for this session, starting with 2 presentations by Qingkai Shi, who is a PhD student in Hong Kong. And his first work is about scaling static analysis. Please, Qingkai, this is your floor.
Okay, thank you. Okay, thanks very much. It is my great honor to have the chance to present my research online. In this talk, I will present our solution to a very important but non-neglected problem, the extensional scalability problem. That is in face of many software bugs, how we efficiently check them together. This talk has 4 parts: the background, the approach, and an evaluation, and a brief summary. So although many bug detectors have been deployed and we already have many achievements, we still suffer from many software bugs in our everyday life. These bugs may be caused by invalid use of memory, such as double-free, user-free, null-point dereference. These bugs also include many taint issues, such as secure injection and command injection. We call these software bugs value flow problems. Generally, we say the value of a variable x flows to the variable y if x is assigned to y directly through an assignment or indirectly via some point operations. A value flow problem means that a value improperly flows to some sensitive program statements. Here is an example where a null pointer flows to a dereference statement through 2 variables, p and q, causing a null point dereference bug. So to perform a value flow analysis to detect the value flow problems, we need to build precise value flow graph based on a very precise pointer analysis. So this technique is published in PLDI 2018. And with the precise state dependence graph or value flow graph, the next step is to search invalid value flows on the state dependence graph with the help of an SMT solver to solve path conditions and prune infeasible paths. So the problem we addressed in this paper is how to efficiently check multiple bugs at the same time. And in the next talk, I will present our technique on how to improve the parallelism of existing parallel designs. We will also present our approach to fast SMT solving in ISTA this year. So in an industrial setting, static analyzers often need to check many problems at the same time, which will be very time and memory consuming because more program states need to explore and there will be more computation redundancy. The main problem is that the analysis logic of checking different problems are independently between each other, which leads to redundant graph traversals on the state dependence graph and unnecessary invocations of the expensive SMT solver. Our work is an interproperty-aware analysis, which uses the analysis results of checking one problem to speed up the analysis of other problems. The basic idea is to utilize the mutual synergy among different value flow problems to reduce unnecessary graph traversals and SMT solving. So we observe the mutual synergy among different value flow problems are many in the forms of path overlapping and path contradiction. For path overlapping, let us look at the example where we aim to detect memory leak bugs and free global variable bugs on the state dependence graph on the right. To detect the memory leak bugs, we need to search paths from a heap pointer to free statements. To detect free global variable bugs, we need to search paths from a global variable to free statements. Assume that we first check the memory leak bug from the heap point A by searching paths from the heap point A. During the graph traversal, we record the information that the vertex C cannot reach any free statements. We use this information to speed up the analysis of the free global variable bug. When checking the free global variable bug from the vertex B, we can directly stop at the vertex C because we have known that C cannot reach any free statements. This is an example of path contradiction where we attempt to check memory leak bugs and null point dereference bugs. For both bugs, we need to search paths from the vertex A. Because A is the return value of a function malloc, the function may return a heap pointer when it succeeds in locating a memory space, or a null pointer when it fails. We use the condition A is not equal to 0 to represent the heap pointer, and A is equal to 0 to represent the null pointer. During the path traversal, we need to check whether the path condition conflicts with these bug-specific conditions. For instance, when traverse the graph for checking null dereference bug, at the vertex B, we will use an SMT solver to check whether the path condition gamma conflicts with the null condition. Assume that the path condition gamma is satisfiable but conflicts with the null point condition. According to this information, when checking memory leak bugs by searching paths from the vertex A, we can directly determine the path condition gamma doesn't conflict with the heap point condition without invoking the expensive SMT solver. So this is the workflow of our approach. The input is a specification of value flow problems to check. Each specification mainly consists of 3 parts: the source vertices, the sink vertices that determine what kind of value flow paths we need to search on the dependence graph, as well as specific conditions each bug type needs to satisfy. With the specifications, we make optimization plans so that the subsequent graph traversal engine can utilize the mutual synergy for shoring or pruning paths for detecting different value flow problems. In the evaluation, we use 22 programs from the standard spec benchmark and GitHub. The sizes of the programs range from a few thousand lines of code to 2 million lines of code. We compare the time and the memory cost of our approach Catapult with 3 industrial strength tools: Pinpoint, a value flow analyzer where our approach is built on, and Clown and Infer are powered by LLVM and Facebook. Due to time limit, we only discuss the results of comparing to Pinpoint in this talk. The figure on the left illustrates the results of comparing our new approach to Pinpoint. The x-axis is the benchmark programs ordered by their sizes, and the y-axis is the time and the memory cost. The black lines are the time and the memory cost of Pinpoint, and the red lines are the cost of our new approach. Compared to Pinpoint, the new approach is 8 times faster, but only consumes 1/7 memory. Sometimes Pinpoint exhausts all 200 GPU memory and races out of memory exception. In comparison, the new approach never exhausts the memory. We also draw the growing curves of the memory and time cost against the number of value flow problems to check. We observe that the time and memory cost grow much slower than Pinpoint, so we believe the new approach is more scalable with regard to the number of value flow problems. So as a brief summary, to address the extensional scalability problem, we propose an inter-property-aware analysis that utilizes the mutual synergy among different bug types to accelerate bug finding. Okay, thank you very much. This is the first talk.
All right, thank you, and thank you for the very thorough timekeeping. I will now go on Slido to see if there are questions. There's no question yet. So I would have one. Can you go back to the comparison slide? So just like one, yeah. Just the one after that, yeah. So in your opinion, so here we see a drastic improvement in time, in particular the fact that Pinpoint sometimes cannot finish. How do you explain their poor performance in time? What's the key feature of Pinpoint that prevents them from finishing on the big programs?
Because we actually checked 20 value flow problems together. So for each value flow problem, Pinpoint detect them independently. So because for each value flow problem, pinpoint will exhaust a lot of memory. So for 20 value flow problems, that will exhaust all memory. So it cannot finish checking.
Okay. Okay, and now we have a little bit of time and no other questions. So can you also summarize the comparison with the two other tools? Because I'm not sure I understand how you compare to CLang and LLVM.
Yes, I have some backup slides.
Okay.
Yeah. So I also compare to Clang Static Analyzer, which is a symbolic execution-based tool. I compare two versions of Clang. A default version that uses an imprecise and range-based solver to determine path feasibility, and a full path-sensitive version of Clang, which uses Z3, a precise and full-featured SMD solver to determine the path feasibility. And we also compare to Infer, an abstraction interpretation-based approach.
Mm-hmm.
So we observe that catapult, our approach, is much faster than the full path sensitive version of Clang, and has similar time and memory cost with the default version of Clang and Infer. With similar time and memory cost, since our approach is full path sensitive, but the default Clang and Infer is not fully path sensitive, so our approach have much higher precision, and it has much higher precision than others, reporting less than 30% false positives.
All right, thank you. No questions from the audience on the chat as far as I can see. And it's now time to go to the second presentation. So thank you very much for this first presentation. And now you will go on to present your second piece of work, which is about pipelining bottom-up data flow analysis.
Yes.
Yeah, we see the presenter mode here. All right, thank you. So you got 10 minutes.
Okay. In the second talk, I would like to introduce how we parallelize our static bucket detector via a pipelining technique. The title of this paper is Pipelining Bottom-Up Data Flow Analysis. So this talk also consists of 4 parts: the background, approach, evaluation, and a brief summary. So in practice, to run in parallel, conventional approaches are often implemented in a bottom-up manner. In a bottom-up analysis, callees are analyzed before callers, and the analysis results of a callee function are recorded as function summaries, which summarize the function behavior. For example, we have 3 functions where function f calls the function g and h. So we firstly analyze the function g and h, generating function summaries by recording whether they will return invalid pointers. With these summaries, we then analyze the caller function f to check whether the invalid pointer may be improperly used. Bottom-up analysis is very easy to parallelize. This is because functions without calling dependence can be analyzed in parallel. So in the example, we can analyze the function g and h at the same time and then analyze the function f. However, as pointed out by the recent studies, the parallelism is very limited. As shown by the graphs, the x-axis is the running time and the y-axis is the CPU utilization rate. We can observe that the CPU utilization rate drops off at the second half of the analysis. This is mainly because the call graph is usually a tree-like graph. The bottom half of a call graph is usually very sparse and so has sufficient parallelism. However, the top half of the call graph is usually very dense, so the parallelism is limited by the calling dependence. So a natural question here is there any chance to improve the parallelism so that the analysis can finish earlier, just like the red curves? Intuitively, it is not necessary to start the analysis of a function until we get all the analysis results of its callees. So our basic idea is to relax the calling dependence between functions. Ideally, we can partition the analysis task into multiple parts so that they can be pipelined as shown by the graph. The remaining problem is how to partition the analysis of a function. Before introducing the partition method, let us look at what kind of function summaries we need to generate for value flow analysis. Here we use the null point analysis as an example. Given a function, null point may come from three places: from a caller function via the function parameter, from the current function, or from the callees via the function return value. So according to where a null point may come from, we generate three types of function summaries. Type 1 summary is the value flow starting from a parameter, and type 2 summary is the value flow from the null point in the current function. Type 3 summary is the value flow from a null point returned by callees. So here is an example where function foo calls the function bar. The red part is the dependence graph of the function bar, and the black part is the dependence graph of the function foo. Following a conventional bottom-up analysis, we analyze the callee function first and generate two summaries. The type 1 summary, which is the value flow from the function parameter A to the return statement. The type 2 summary, which is the value flow from a null pointer to the return statement. Second, we analyze the caller function foo, and using the summaries we generate. We generate a type 2 summary for function foo and a type 3 summary for function foo. One is the value flow from the null pointer in the current function to return P, and the other is from the null pointer in the callee function to return P. So in our approach, we partition the analysis task of a function into three parts. Each part generates a type of function summaries. Given a pair of functions where function foo calls the function bar, a conventional approach conservatively assumes that all the analysis tasks in the caller function depend on all analysis tasks of the callee function. So we need to finish all tasks in the callees and then start to analyze the callers. So however, we observe that not all such dependencies are necessary, as the rate dependence relations actually can be removed. So we have opportunities to improve the parallelism. Let us look at the example. We can observe that the type 2 summary of function foo depends on the summary of bar. That is, the blue path in the figure goes through the yellow path from the function bar. So the black dependence is necessary. The blue path doesn't go through the type 2 summary, the yellow path of the function bar, so the red dependence is not necessary and can be removed. After removing the red dependencies, we can schedule them in a pipeline manner. After generating the type 1 summary of bar, we can generate the type 1 and type 2 summary of function foo. And finally, we can generate type 3 summary of function foo after generating all summaries of the function bar. So for this example, our approach doesn't need to wait the analysis of function bar to start the analysis of the function foo, so the new parallel design is much more efficient. In the paper, we formalize our pipeline idea in the IFDS and the IDE framework for a wide range of problems, such as the NSS problem, the problem of securing information flow, and so on. These problems have a common feature that they can be reduced to a graph reachability problems, just like our value flow analysis. As for evaluation, we use similar benchmark programs as before and compare the pipeline approach to the conventional parallel design in terms of CPU utilization rate and the speed up. These figures show the CPU utilization rate for analyzing some of our benchmark programs. The red curves are the CPU utilization rate of our pipeline approach. The blue ones are that of the conventional approach. It is clear that our approach has higher CPU utilization rates than the conventional one, and so can finish the analysis earlier. This figure shows the speed up against the number of threads. Different lines represent the speed up of different benchmark programs. With more threads, the benefits of our approach is more apparent, leading to 2 times to 3 times speed up. Such a speed up is not trivial in practice. It is enough to make an originally impractical analysis practical. For instance, originally an analysis may need 12 hours. With our approach, it may only need 4 hours to finish. For the pipeline approach, there are 2 factors that may affect its performance. First, we have shown that with more threads, our approach is more effective. If we only have only one thread available, neither of our approach and the conventional design can perform parallel analysis, so they will have similar performance. Second, the effectiveness of our approach is also affected by the sparsity of the call graph. Recall that our pipeline approach relaxes calling dependence to improve the parallelism. So if a call graph is very sparse and has little call dependence, then the benefits of our approach were not that apparent. So as a brief summary, our approach relaxes the calling dependence to improve the parallelism of bottom-up data flow analysis. So to take advantage of multi-calls, let us pipeline not simply parallelize your data flow analysis. Thanks very much. That's it.
Thank you very much for the very good talk. We have one question. How to generalize the partitioning of summaries to other kinds of problems beyond null pointer dereferences?
Let me, we actually generalize our approach to any problem in IFDS or IDE framework. These problems can be reduced to graph reachability problems. So any analysis that can be reduced to graph reach problem can use our approach.
So you mean that because the summaries are not specific to any kind of problem. Is that what you're saying? So if you go back a couple of slides.
About the summaries?
Yeah, about the summaries, yeah. So when you have the example, yeah, here.
Yes.
So type 1, type 2, type 3, they're not specific. What you're saying is that these summaries are not specific to a kind of analysis.
Actually, we are checking some problems that can be reduced to graph reachability problems. So that we'll have some sources and some destinations on the graph. So if you can identify the sources and the destinations, then you can generate the summaries like this. So the null pointer here is the sources, right?
Yeah. Second question. I'm curious whether the partition of the caller's callees can induce imprecisions in the results. Have you observed any such cases?
No, actually, it doesn't. It will not introduce any precision because we can prove the correctness of our approach.
All right. Well, thank you very much for those 2 very good works and for those 2 very good presentations. They were very clear. We will now go on with the next presentation, which is about Oracle improvement, and that will be given by Gunel Jahangirova, who is a postdoc at USI in Switzerland.
Hi.
Hi, Gunel.
So as it was mentioned, I'm Gunel Jahangirova, and today I'm going to present our work, an empirical evaluation of Oracle improvements that has been recently published at IEEE Transactions on Software Engineering. So in a typical software testing scenario, we have a software and a test. We generate and execute test inputs over that software, and then we get test outputs. At this point, we need a mechanism that will tell us whether these test outputs are correct or not, and this mechanism is called an oracle. When evaluating the correctness of test output, an oracle should report all faulty behaviors, but only faulty behaviors. To explain this further, let's have a look at an example where we have a method that finds the maximum of two integers, and it has an assertion oracle that claims that max should always be greater than a. If we execute the test case of 0, 0 of this code, we will see that this assertion fails while there is actually no bug in the code. Therefore, this assertion oracle does not expose only faulty behavior, and this test case is actually an evidence of a false positive. Continuing with the same example, now we have a different assertion oracle, but let's say our method has a bug in it which makes max to be equal to b plus 1 instead of b. If we run a test case of 0, 1 here, the value of max would be 2, but our assertion oracle will not notice this because the max is still greater or equal to b. Therefore, this assertion oracle is not able to expose all faulty behaviors, and this test case combined with this fault is an evidence of a false negative. So this notion of false positives and false negatives lies in the heart of our approach for oracle assessment and improvement, called shortly OASIS. And the idea behind OASIS is that we have initial assertion oracle, we pass it to OASIS, and OASIS generates the evidence of false positives and false negatives, as shown in the examples before, using test case generation and mutation testing. It then passes this evidence to the developer, and the developer is responsible with coming up with an improvement state that would improve the assertion so that it does not have these false positives and false negatives. So this is an iterative process, and as human is in the loop of this process, whether this automated assessment approach and semi-automated improvement approach is useful for developers is an important question, which we have tried to address in the work that I'm currently presenting. So for this purpose, we have conducted two studies. The first one is the assessment study. And here, the idea was that if the developers are able to manually detect these false positives and false negatives easily, then our automated approach does not provide much value. And to analyze that, we have conducted experiments with 39 developers. And each developer received two assertions, two Java classes, and each Java class had 3 assertions in it. We conducted these experiments in 3 different sessions, and each session started with a training, followed with the actual task. And in the task, we asked the developer to indicate for each of 6 assertions whether, in their opinion, it has a false positive, false negative, doesn't have any of those, or they could pick an option of I don't know. Then this was followed by a final questionnaire. This chart shows a brief overview of our results. So we can see that overall, developers are not very good in doing this task, as they did it correctly only in 30% of cases. And we can also see that professionals, their performance was almost twice better than the one of students. The second study we have conducted is improvement study. And here the idea was, what if we tell the developer that this assertion oracle has a false positive or a false negative? Will he or she be able to come up with an improvement step that would remove those? And for this, we recruited 29, another set of 29 participants, and we divided this pool of participants into 2 groups. The first one is the manual, so they did the improvement process manually without the support of any tool, and the second one used OASIS for this task. Here, each developer worked with 1 Java class, and this Java class had 2 assertions in it. The first one had a false positive, the second one had a false negative. For this experiment, we have conducted 1-to-1 sessions. So we had 29 sessions overall, and each session started again with an initial training, followed by a practice task. Then the group that used OASIS received the training on the tool, and then the participants proceeded with the final improved task, followed by a question. So we report the results for this improvement study using 2 notions. The first one is fully correct, which means that the final improved assertion had no false positives and no false negatives. And the second one is partially correct, which means that there were no false positives, but some false negatives were allowed. So we can see from this chart that the improvement process was more successful with OASIS. As for both assertions, the developers were able to achieve full correctness in more cases when they were using OASIS. So, of course, what I've been presenting so far is a very brief overview of our paper. So if you're interested in details, which I hope you are, please go and check the full version of the paper. Also, if you're interested in Oracle problem and Oracle assessment and improvement in particular, you could check our previous work and our very recent work that will be presented at FSC 2020 very soon. Spoiler alert, in this work, we have replaced the human in the loop with a genetic algorithm, and the improvement process is performed automatically. The source code of OASIS, as well as all the data sets that we have conducted during these human studies, is available publicly on the GitHub page of OASIS. And with that, I'm done. I thank you for your attention, and I'm happy to take any questions.
Thank you, Gunal, for the presentation and for the good timekeeping. I'm checking on Clouder, no questions yet, so I would have one. So in all the tasks, the participants had one or two classes and a couple of assertions. Which kind of program was that? Was it like this example you showed, like max or addition, like simple arithmetic?
Okay, no. So for the examples I've shown are very simple. So this was not what we have given the developers for the task. So for the assessment study, they were given 3 Java classes. One was the implementation of matrix and operations on it. The second one was the implementation of stack, an array-based one. And the third one was a poly function. So it was a class about doing the polynomial functions. For the improvement study, there was only one class used, and that was the stack class again. So 2 methods, top and pop, they had to come up with the assertions for these 2 methods. So they were not extremely complex, of course, because there is a limited amount of time for these tasks, but they were not as simple as the ones shown on the slides.
Okay, but all of them were self-contained. I mean, it was one class that contained all the code.
Exactly.
Okay. Thank you. I will check if there are other questions. No other question. Oh yeah, and time has passed. Okay, it's really short. Thank you very much again, Gunel, for the presentation. And oh yeah, one new question: did you consider your tool on more line of code, scalability of the approach?
Yes. So the assessment of our tool is done in this work, in test Oracle assessment and improvement, and we have evaluated it on many different classes, around 150 of different sizes, and it seems to scale well. But as mutation testing is involved, and if there are many mutations generated, of course, the cost becomes a bit. So it takes longer to find the evidence of false negatives sometimes if there are many mutations.
Thank you very much. So we now move on to the next presentation by Roman Haas, who is an industry PhD student at CQSE, a German company, and he will talk about the identification of unnecessary source code. Roman.
Yes, I would like to share my screen, but I can't.
Gunel, can you stop sharing your screen? Yeah. And now it should work, right?
Thank you.
Roman?
Here we go.
Yeah,
so
thank you very much. So
welcome to the presentation of our TOSM paper on the question whether static analysis is able to identify unnecessary code. And unnecessary code is code in which no stakeholder has an interest anymore. For example, because features have been re-implemented or the stakeholder interests have changed over time. And it's important to note that it's not the same as unreachable code, because technically unnecessary code can still be reachable. And it's also not the same as unused code. For example, disaster recovery code might be unused, but still necessary. The problem with unnecessary code is that it wastes resources. For example, the familiarization with a code base is harder if there is unnecessary code, and it makes also testing and compiling of the application requires more effort. It also increases the attack surface of an application as well as the binary size. And last but not least, in case of migration scenarios or code certifications, unnecessary code can increase the required effort. So we want to get rid of unnecessary code, but first we need to identify it. And a common approach would be to record usage data on production systems and identify unused code and ask developers whether they want to delete it. Unfortunately, this meaningful production data is typically not available in practice, and recording it would require too much time when the question of unnecessary code arises. That's why we investigated in our TOSEN paper an approach that simply relies on the source code and its history, and derives from this information within seconds recommendations and suggestions on which code might be unnecessary so that developers can investigate them further. The main idea behind our approach is that unnecessary code is stable, that is, files have not been changed in the recent past, and decentral. We use the last criterion to differentiate between unnecessary code and very core features that are typically also not changed that often. The data sources that we use are the version control system, where we check for each file when it has been changed. And we use the dependency graph of the system to calculate centrality measures. I give you an example here. So we see the dependency graph of a software system. We see the files and the code dependencies between those files. Now, using the analysis of the histories, we can identify stable files, so those that have not been changed in the recent past. They are labeled with an S here on the slides. And using, for example, an algorithm like PageRank, we can identify for each file how central the file is, and also identify the most decentral files. And only those that are stable and decentral at the same time are recommended as potentially unnecessary to developers, so they can decide whether they want to take action on them and delete them. We evaluated our approach, and the biggest challenge of this evaluation was finding the ground truth for a file. So is it actually unnecessary or not? And in our evaluation, we used 3 different oracles to answer this question. The first one is, again, the history of the software systems. So we tried to find cleanup commits where actually unnecessary code has been deleted. And for the previous version of the system, we generated recommendations and checked whether the recommendations matched the deletions of the cleanup. The second oracle is usage data. For some of our study subjects, we had meaningful usage data, and we checked whether our recommendations for the system actually correspond to unused code. And in the end, developers have to decide whether code is actually unnecessary. So we also asked them whether they agree with the recommendations of our approach. For the study, we used 14 study subjects from open source and closed source, and those were written in different programming languages. And for some of the study subjects, more than one oracle was available. Here in this presentation, I will present you the core results, the precision of the of our approach, and the values here vary greatly between the oracles, and I will briefly explain why. So for the cleanup commits, we found only a precision of 3%, so that's a quite small value, and we found that in practice those cleanup commits are very small, so only a handful of files is deleted. And this leads to a small precision value for us. Quite the opposite was true for usage data. We found that 99% of our recommendations were not used in production systems, which is a quite good result. And in the end, developers agreed with 34% of our recommendations. Moreover, they actually deleted 20% of the recommendations shortly after our interviews. So here we had real-world impact. The summary is code stability and code decentrality are able to identify unnecessary code. And they are no perfect predictors, as one can expect when using such a simple approach as we did. But even though the approach was simple and the idea was basic, we had real-world impact because developers deleted code based on those recommendations. feel free to contact us if you want to know more about unnecessary code and the identification and deletion of it. Thank you. So I would be open for questions now.
Yeah, sorry, I was muted. Yeah, thank you very much, Roman, for the presentation. What is usually the percentage of code that turns out to be unnecessary?
If we only knew. In the literature, there's no study on large systems where developers investigated the whole code base. We only had a small sample set. Our approach is designed to generate only a handful of recommendations, so it's still usable in practice. And for those, we had a precision of nearly 1/3 of the recommendations. But for the usage data, I can report that we have seen for some study subjects that half of the files were actually not used over years. So half of the code base is actually unnecessary, could be unnecessary. We don't know, but actually they are not used.
They're not used, or they're not modified?
Not used in production.
All right, interesting. Lots of questions. I'll take the second one, and then please, we'll do it offline. So are there levels of unnecessariness? Wow.
For sure. Our approach is designed to find big chunks of unnecessary code. So we try to cluster them by the package hierarchy, for example, so that we can find large features that are not being used anymore. That was a level of unnecessity for us. So finding big pieces. And in our discussions with the teams, we also realized that some, for example, migration code that stems from migrations that were needed years ago, those are not very necessary, but developers tend to keep them. Other code that is actually just playground from years ago is unnecessary and is deleted. So I would say, yes, there are different levels.
Thanks a lot. Roman, your talk and work has raised a number of questions on the chat. Please, for all of you who are asking those questions, please contact Roman directly, either by email or by in a private room, because we have to move on to the next presentation. So thank you very much for the questions and for the answers and for the presentation.
Thank you.
And we will go now to the next presentation by Mohammad Ganavati, who has recently graduated. This work was part of his PhD, and he now works in industry, and he will present his work on repairs of leakage in Java projects. Very good. Mohammed, we don't hear you.
So now you can hear me.
Yes, now you can. Yeah.
Perfect.
So please go ahead. You have 6 minutes to present your work.
Yes, I will. Okay. Hello, everybody, and good morning. I'm Mohammad Ganavati, and today I'm presenting our empirical study on the resource and memory leaks and the repairs, which was published last year in EMZ. At the time of the publication, this was a collaborative work, including 4 members of Heidelberg University and David Lowe from Singapore Management University. Of course, in this very little time, I cannot go through all detail of the work, so I encourage you to look at the work at the journal website. A questionnaire with Microsoft engineers in 2015 showed that the leak detection is still one of the top challenges for practitioners. But why this is still a top challenge, even with having in mind that there are so many works are already published in leak detection? One approach is to look at the bug repositories and try to get more information and insight about the problems facing to the developers. For example, with answering questions such as, how are the leaks detected? How many files are modified to fix a bug? Are there any common patterns in detection, root cause, and bug fixing? The result may help us to find probably the gaps, and also can be a guidance for future research and diagnosis of leak-related bugs. We also realized that there are not so many comprehensive studies on leak-related bugs which can answer all of these open questions. Therefore, to fill this gap, we conducted an empirical study on resource and memory leaks and also the repairs. Yeah. Of course, as you know, for a valid empirical study, we first need to design a proper methodology. So for this work, we selected 15 projects from two most popular repositories for Java projects, namely Apache and GitHub. And then from the issue repository of each project, we selected a specific issues which meet 3 criteria. First, they should contain the keyword leak, they should be labeled as bug, and also they should be already fixed. It is also important to mention that we only discussed those bugs who already reported, but not those bugs who already fixed during the code development, and they are not reported to the bug repository. After clearing the dataset, we obtained a dataset with 491 issues, and then from each issue, we collected different properties such as summary, description, comments, patches, as well as related timestamps. And with this data, we answered the question arising in this empirical study. In the first question, we wanted to find out how are the leaks detected by the users. We found that 2 main methods are common: source code analysis and runtime analysis. As you can see, the runtime detection was more common, and more resource leaks than memory leaks were detected by source code analysis. We also found 2 interesting results. First, in 11% of the cases, the reporter reported the bug with help of a failing test, and only in 1 case, a static analyzer was used to report a leak. However, we cannot generalize this specific part because maybe developer already used the static analyzer during the code development and fix the bugs who could be found by a static tools. So with this question, we could find that the runtime detection is still dominant detection type for memory leak bugs, for memory and resource leak bugs. The second question, we look at the root cause of the leak-related bugs, and we found that about 80% of the leaks were caused by 4 major root causes, as you can see in the red box. More interestingly, we found that in about 76% of all cases, the leaks were manifested in normal execution path. That is execution path in absence of exceptions. We also analyzed the patches to see if there are any common patterns in fixing leak-related bugs. And we found 13 code transformations, which were used to fix about 57% of the memory and resource leaks. Here you can see an example, a simple example of a memory leak issue, which developer just changed a variable type from a static to non-static. And from this specific type, we found 4 cases in our data set. You can take a look at our paper for see more type of this transformation. So this question showed us that it is possible to extract patterns from bug fix history. We also investigated the bug fixes to find how many files were modified. And we found that in about 54% of the cases, only 1 file was changed. And in only 12% of the cases, 3 or more files were changed to fix the bug. Therefore, you can see that the leak fixing bugs are leak-related bugs can be fixed with high localization. To conclude my talk, let us summarize some key points which we have learned from this study. First, by analyzing the bug history, we can find some good practices to avoid recurring leaks, maybe some like check leaks for developers. Second, in some cases, the user could detect the leak via failing test, and this can motivate automated test generation, specifically for leak detection. We also analyzed the bug fixes, and we found that the bug fixes are highly localized, which is an interesting result for automated program repair, because this is the first step toward automated program repair. And last not the least, we found that also there are common patterns in bug fixing. So template-driven patch generation can be one way of fixing leak-related bugs. And with this point, I would like to thank you for your attention, and I'm happy to answer your questions.
Thank you very much, Mohammed, for the big presentation. So there is one question. Can you please clarify what do you mean by leaks? Are there bugs in source code, or are they static bugs or runtime bugs?
No, they are the bugs. The bugs which are in source code. It can be different type. Yeah, it can be source-related bugs like open files or open connection and so on, which we divided them as which we classify them as resource leaks, and the bugs who are related to the heap usage. Yeah, so those objects which are used at some point of the code, but they never be used anymore. And they have still references to them within the code, but they are just there, just consuming the heap without any usage. Yeah? These kind of bugs we discuss as we classified as memory leak bugs. So two types: resource and memory leaks, and all of them, of course, in the source code. Yeah.
Thank you. Second question: following the localization analysis, did the repair mostly involve changing a few lines of code?
We had different things. It sometimes was like also adding a new function. For example, at some case, a specific function was not like closing a specific object. Yeah, the close method was not written at all. Yeah, so the developer just wrote again a close function. Yeah, but mostly was a small. In most of the cases, it was a small. Yeah, so code refactoring in a large sense was not the case in many cases.
Thank you very much, Mohammed, for the presentation, and thank you everyone for the questions. We will now go to the last presentation of this session, given by Daniel Martens, who graduated a couple of weeks ago and who will present his work on reviews in stores. Daniel?
Yes?
Yes, very good.
All right. Welcome everyone to the ICSI Journal Fest presentation of our paper, Towards Understanding and Detecting Fake Reviews in App Stores. My name is Daniel Martens and my co-author is Walid Malesh. Now, applications are targeted by fake user feedback to manipulate their ratings and rankings in app stores, and this should either or not mislead specific users to download applications. Now, app store operators, they are already aware of this phenomenon and they prohibit such paid, incentivized, filtered or fake feedback in their policies. However, despite the significant recent research, especially in the area of app store analysis, none of the works has yet considered the implications of fake reviews. And by this, I just want to highlight that we are the first to analyze this problem. We published our results in the Empirical Software Engineering Journal, and our paper is also available open access. Let's begin with an example. What you see here is a regular app review. It was submitted by a real user of the application. It reflects the user's honest opinion, and it was provided spontaneously. Now, on the right side, you see a review for the same application with the same rating of about the same length. However, this is a fake review. Now, fake reviews, they can be submitted either by real or unreal users of the application. The reviews may or may not reflect the user's honest opinion. However, these reviews are incentivized. For example, they are paid. And these fake reviews, they hinder developers from understanding their real users' needs. And to underline the importance of the problem, Google even made a public statement about fake reviews, and that Google talks about problems in public is really rarely the case. So let's take a look at our research method, which we divided into the data collection, preparation, and analysis phase. Now, in the data collection phase, we begin by crawling the app identifiers and app metadata, as for example, the paid price, and then we collected the actual app reviews. And we call this our official reviews dataset. Now, we say official reviews because we don't know if these are fake or regular reviews. And on the other hand, we also try to create a dataset containing only fake data. Now, here we were quite successful. So, through online research and an investigative discrete questionnaire that we conducted, we identified 43 fake review providers and we gathered information about their fake reviewing strategies and offers. And what we notice is that these providers, they can be separated into two categories. We have paid review providers, where you simply pay money to receive your fake reviews. And then we have, as you can see here on the screenshot, review exchange portals. There you sign up, you give a review for the application of another developer, and then this developer writes a fake review for your application. Now, once you decide to sign up on such a portal, a typical fake review request look like this. So we have the application title and the icon, and below is the review that you should publish letter by letter, identical within the App Store. So we have the exact rating, the title, and the review message. And as you can see here already, fake reviews, they do not mean short or low quality reviews, but they are really written to sound authentic. Now, what we notice is that fake reviewers, as a proof, they need to upload a screenshot of the review they submitted to the review exchange portal, and we try to extract those screenshots. Then in the data preparation phase, from these screenshots of the fake reviews, we extracted the text, we filtered for reviews in English language, we removed duplicates, and then we matched the reviews. And this is really important. So we only consider fake reviews that have been published within the Apple App Store and that still exist within the App Store. In the data analysis phase, we then analyzed the market of fake reviews, we identified fake review characteristics, and we came up with a solution for the automated detection. Now, to the characteristics. So we crawled about 60,000 fake reviews, and we empirically analyzed and compared them with 62 million reviews from the Apple App Store. And we also report on quantitative differences between the fake reviewers and also the concerned applications. Now, one interesting finding that we made is that when applying existing App Store analysis approaches to our dataset containing only fake reviews, we were able to extract bug reports and feature requests. And this clearly highlights when not considering or removing fake reviews before further analysis, they will impact the results of our analysis. Now we try to come up with a solution for the automated detection of fake reviews. So we developed a supervised classifier to detect fake reviews. And we conducted what I call in the wild experiment, where we evaluated the performance of multiple classification algorithms, their configurations, and the classification features. And I call this in the wild experiment because we don't know about the actual distribution of fake and regular reviews within app stores. So what we did is, as you can see here on the screenshot, we varied the skewness of the data set, beginning from only 1% fake reviews to 100% fake reviews. Now, to come up with meaningful results, we also took a look at the research of fake reviews in other domains, and these report distributions of 10 to 15% fake reviews. And for this distribution, we were able to detect fake reviews with quite promising results. So we achieved a recall of 91% and an AOC-ROC value of 98%. Okay, I would like to thank you for listening to our talk, and I'd be happy to accept questions now.
Thank you, Daniel, for the very good presentation and for the timekeeping. There's no question on Clouder yet. So I would have one question. So you said that you can you come back a couple to the slide before the classifier? Yeah. So the one here. We also the one before.
Okay.
Yeah, here. We report on quantitative differences of fake reviewers and concerned apps. So can you tell us a little bit about this? Like, what are your findings on the differences of fake reviewers and concerned apps? Did you find like specific kinds of apps which are more prone to fake reviews, or what was
yeah, it's the findings are really interesting, especially regarding the fake reviews. So what we would normally expect is that the fake reviewers, they just write one fake review, then they switch to another account, but this is not the case. So fake reviewers, sometimes they have published 100 reviews with using the same account. And also very interesting is that these review exchange portals, they have really clear policies on how you should submit fake reviews. So I think Apple invests already a lot of effort. So they write that you should, in between, download other applications and not submit a review for these, that you should use the applications you submit fake reviews to for a specific amount of time, for example, that you should not uninstall them directly after you submitted the fake review. And yeah, this is really a chase for the App Store operators against the fake reviewers, and they have a lot of interesting strategies they develop.
Interesting, thanks. Couple of questions. Who are possible users and application area of your tool?
I think everyone that analyzes their app reviews, that receive a large amount of app reviews. So what we noticed in the area of app store analysis is that normally at the beginning we took an isolated look at the feedback of our applications, and there we mostly know if it's a fake review or this is our review. But now we sometimes also we analyze the feedback of competing applications. And for these, we cannot be sure if they receive fake reviews or not. So here, it would really help to remove the fake reviews before. For example, if you try to extract feature requests from competing applications, this could clearly help.
Very good. There are a couple more questions on Slido. You will receive them offline since now we are running out of time. I would like to thank everyone here. King Kai Chi, Gunel, Daniel, Roman, Mohammad, thank you very much again for preparing those presentations, for giving them perfectly on time, for answering the questions. It was a very peculiar setup, but I think it went well. I hope you will get a lot from get some feedback beyond this presentation. Thank you everyone for attending session I-23 on code artifact analysis. Thanks to the speakers. Goodbye.